Okay, great. So we're very happy to have Haoyu Zhang from nearby USC, and he's going to tell us about Fortuity D1D5. Go ahead.
Thank you for the invitation. It's a great pleasure to be here. So today I'm going to talk about two papers with Qiming Zhang and Yixuan. What? Thank you. Okay, so I'll start with the introduction. Holography provides a natural framework for understanding the full microscopic description of black holes. One of the major success, from my opinion, is that the supersymmetric indices reproducing the black hole entropy. But index counting tells us surprisingly very little about the wave functions of the black hole microstates. So today, in this talk, we will focus on a particular feature recently proposed for the supersymmetric black hole microstates by Zhang and Lin, which draws a very sharp distinction between BPS states, even at finite time. The notion of fortuity has been analyzed in various setups into four super YAMLs, SYK, D1D5, ABJ, ABJ. Before I start with the D1D5 fortuity, I'll give a general overview. The holographic CFTs in previous slides are all labeled by a parameter n. At finite n, some states that look independent at large n become secretly identical, for example, by the trace relations of matrices in n-4 super YAMLs. The Hilbert space at finite n is a quotient of Hilbert space at n equal to infinity by certain equivalence relations. I'll provide an example, but one equivalence relation is a trace relation in n-4 super YAMLs. And all these equivalence relations are related by inclusions. This means there are more relations at a smaller n. The first class of BPS states is the so-called monotone states. These states are BPS for all n, meaning their BPS property does not change as n varies. In other words, their BPS property does not change as the gravitational coupling G Newton varies. So these states have a well-defined large n limit. So you can follow these states to infinite n, and they can be disassembled into a product of gravitons. The second kind of class are the states that we are going to focus today. So these states are only BPS below a critical n star. And they satisfy the following equation. Here I'm using the supercharged action that sequence of operators equal to in star. One condition for them being BPS is Qx on the operator is 0. So let's start with Q action, but I will be more precise in the later part of the talk. This in star is an element of the equivalence conditions. So this means for all the n smaller or equal to n star, Q act on O(n) is 0. So this means this sequence of operators are only BPS when n is smaller than n star. So here I drew a picture. You can think about this dot as a BPS bond, and here I'm following n. So when n is below n star, this sequence operator just satisfy the BPS bond. However, after a critical point, these states no longer satisfy BPS bond. So they will become non-BPS as you vary n. One concrete example of in star is a trace relation in n-4 super YAMLs with gauge group Un at n-2. Here, there are three operators. The first one is single trace, two traces, and three traces. These operators are independent at n bigger than 2. However, when you go to n equal to 2, these three operators are linearly dependent. This is what I mean by trace relation. So, in summary, fortuitous states become non-BPS as gravitational coupling decreases. In other words, increases. This is a key contrast with monotone states, which survive to large n as a product of gravitons. So let me mention the proposal in Zhang and Lin's paper. They propose that all the fortuitous states account for the black hole entropy, while the monotone states account for the entropy of smooth horizonless geometries. Here, I draw black hole as a black dot and smooth horizonless geometries as some Lego model because it does not have a horizon. In this talk, I will focus on the Fortuity phenomenon in the D1D5 system. This is a CFT that sits at the modular space of symmetric product orbifold of T4, and it's dual to string theory on ADS3 times S3 times T4 with Q1, Q5 units of remote flux. Large families of bulk solutions have been constructed in this setup and can be holographically described by D1D5 system. Therefore, this makes D1D5 CFT actually a suitable lab to test Zhang and Lin's proposal. So there are many contributions to this program. I probably didn't list all the authors. Here actually I've more or less finished a short review of Fortuity and give. So if you have any questions, feel free to interrupt me during the talk. Okay, so the plan of the talk is I will review the Hilbert space of symmetric product orbifold of T4 first, and then discuss what are the BPS states in this Hilbert space of symmetric product orbifold. Then I will turn on the deformation and discuss what's the finite BPS spectrum in the D1D5 system. And after we have some understanding about the finite BPS spectrum, then I'll define what's monotone fortuitous cohomology classes in the D1D5 system. And in the end, I want to mention two aspects of fortuitous states. The first aspect is the so-called R-chart concentration. Basically, this states that all the fortuitous states have a phase right-moving R-chart, which is different from the monotone states because the monotones have R-chart that right-moving R-chart that could vary. I'll also mention an interplay between fortuity and global symmetry. Okay, so let's start review the symmetric product orbifold. So symmetric product orbifold of T4 is we start with n copies of T4 sigma model and gauge this tensor product theory by the symmetric group Sn. Here, when I refer to a T4 sigma model, what I have in mind is 4 compact bosons and 4 left-moving free fermions and 4 right-moving free fermions. The orbifold, the symmetric product orbifold Hilbert space is a sum over twisted sectors and untwisted sectors, which in turn, each sector can be labeled by the conjugacy class of Sn. So here I write the orbifold Hilbert space as a direct sum over different sectors labeled by the conjugacy class, and each conjugacy class in turn can be written as a direct sum over Hg. I will explain Hg in the next slide and further do Sn invariant projection. So what is Hg? So we start with the tensor product theory. We can quantize this tensor product theory on the circle S1 with the following twisted boundary conditions. We take the ith copy xi. We go through the circle by 2 pi. It does not return back to the ith copy, but instead it maps to the gith copy. Here, my notation gi means that the group element of Sn sending the ordered lists 1, 2, 3, 4 dot dot n to G1, G2, Gn. Therefore, you can get a spectrum of this quantization. And in general, the group element G of a symmetric group can be factorized into the product of different cycles. Each cycle is a permutation that sends AI to AI plus 1. Therefore, this means that Hg will actually factorize this into tensor product of single cycle Hilbert spaces. With Hg in mind, let me explain what's H bracket G. So the conjugacy class G bracket of Sn is in one-to-one correspondence with the integer partition of n, which can in turn be labeled by a cycle shape P. Here, I will provide an example. For the integer partition n equal to summation of NW times W. NW denotes the degeneracy of a cycle with length W. Here is a better way of representing it. So there are N1 length 1 single cycles, and there are N2 length 2 single cycles. As we explained in the previous slides, Hg can be written as a tensor product of single cycles, the Hilbert space of single cycles. And H bracket G Sn can actually be written as a symmetric tensor product of the single cycle Hilbert space. I think it's a good plan for me to explain what's the spectrum of the single cycle Hilbert space. So we can think about this single cycle Hilbert space with length W as quantize the T4 CFT on the circle S1 with radius W. Therefore, you will be spanned by fractional modes acting on the corresponding ground states. Good. Now I more or less will conclude my introduction of the normal Hilbert space. Then I will go to the, restrict to the BPS sectors. So there are 8 supercharges, include 4 common 4 in this symmetric product orbifold. If you pick one of the supercharge, and here I pick a right moving right supercharge, and I look at the anti-commutator between Q and Q dagger, they satisfy the following linear relation. So the BPS condition is simply this condition being satisfied. So in the future, when I refer to half BPS states, I will refer to states. So the eigenvalue of L0 tilde and K03. For this, I will denote as H or H tilde, depending on whether it's right moving or left moving. And the eigenvalue of this one, I will denote as J or J tilde. So also up to left or right moving. So half BPS states in the symmetric product orbifold states, I will refer to as states that satisfy the BPS condition in both the left moving sector and the right moving sector. And the quarter BPS states, at least one part will be broken, but another will be satisfied. A more detailed half BPS state introduction is that so for each single cycle, you can construct 16 BPS states. Each of them have holomorphic weight or anti-holomorphic weight proportional to the length of this single cycle. So with this single cycle BPS states in mind, you can take the product of the single cycles and construct multi-cycles as we did in the introduction. The quarter BPS states are the states that we will be interested mainly focus on in this talk because they preserve the least amount of supersymmetries in this system and they are relevant for describing black hole microstates. I will focus on states that are satisfying the right moving BPS condition. Namely, I will have excitations on the left moving part to break the left moving BPS condition. Okay, good. Here I finished the review of the symmetric product orbifolds. So if there are no questions, I will start with the D1D5 system.
So what sector of the Hilbert space were you working on the previous slide?
Oh, here is a half BPS.
I mean, which twisted sector?
Sorry?
Which twisted sector?
Oh, I see. So I'm trying to give a very general construction. So this W, if okay. So as I mentioned in the previous slides, so each twisted sector on twisted sector can be labeled by this integer partition. So I'm focusing on one of them, and as you construct one of them, you can take a product of all of them and construct the Hilbert space. So I was just trying to explain what's the half BPS state sector for the single cycle BPS. And similarly for the quarter. So thanks for the question. D1D5 system is given by deforming the symmetric product orbifold theory by an exactly marginal operator. So this operator is in the twisted sector, and this deformation can break the orbifold structure, as I will explain. I will provide more intuition in the next slide. So the reason why we have to do this deformation, one of the reasons at least, is that at the symmetrical product orbital point, the degeneracy of the low-lying equality BPS states grows exponentially with respect to the energy, in contrast to the sub-exponential growth that's expected in the supergravity. So it's believed that this exactly marginal deformation will give most of these low-lying states anomalous dimensions, therefore rendering the BPS spectrum compatible with the supergravity interpretation. In the later part of this talk, we will show that at least in the finite, this folklore is correct. Okay, good. So this is the effect of the deformation. So now we want to compute the lifting matrix for this orbital, the BPS states. I guess. Right. So the point is that some quarter BPS states can get anomalous dimensions and become non-BPS. So the anomalous dimension of 2D CFT can be written as a summation of the holomorphic and anti-holomorphic anomalous dimensions labeled by delta H and delta H tilde. The difference between delta H and delta H tilde is the anomalous spin, and because there will be no anomalous spin, so therefore it means delta H equal to delta H tilde. So if one wants to compute the anomalous dimension, one can simply focus on computing one of these. In this talk, because we are focusing on the right-moving orbital BPS states, so we will compute the right-moving anomalous dimensions. Because there will be some simplifications. So delta H tilde, as we recall in the previous slides, can be written as a difference between the L0 tilde and the K03 tilde, which is a right-moving holomorphic weight and right-moving L charge. So which in turn can be written as the anti-commutator between supercharged action and Q dagger. So in this talk, we focus on the second-order conformal perturbation series for the lifting matrix. And I can make some general comments why further higher-order corrections are not necessary to discuss. And by the standard Hodge theory argument, that the space of BPS states is isomorphic to the space of supercharged Q cohomologies. A Q cohomology refers to states that are Q-closed, space of states that are Q-closed, quotiented by states that are Q-exact. Good. So let's look at what's the effect of the deformed supercharged action. There are two effects of the supercharged action. So the first one is join. So given an operator that's if there are two cycles within the total cycle shape, so the Q action can join the two single cycles into a longer cycle. Another option is to split, which means that if you have some single cycles within the construction of that particular state, you can split the given cycle into the product of two different cycles, as long as their total length remains the same. So in this talk, because of the computation restrictions, I will only talk about the Q cohomologies or the lifting matrices at n-2 or n-3. But this is kind of enough to determine what are the fortuitous states and what are the monotone states at n-2. Good. So I need to introduce this slide because I want to use the supercharge to write down the supercharged quotient complex. There are two different cycle shapes at n-2. One is untwisted sector, one is a twisted sector. You can think about this untwisted sectors as that the condensation condition of the single cycle does not change. So as you go through the circle by 2 pi, it maps to the original copy. So one can refine the states with cycle shape 1,1, which is in the untwisted sector by the diagonal Clifford algebra generated by the free fermions to 4 different Clifford quartets. One useful way to think about these 4 different quartets are because now we have 2 copy. Essentially, we are doing a Z2 orbifold. So we want our orbifold states to be Z2 invariant. So there are 2 ways. One is to make left moving Z2 symmetric and right moving Z2 symmetric. Another option is to make the left moving Z2 anti-symmetric and right moving Z2 anti-symmetric. And we denote the Hilbert space of the state with cycle shape in the Tweety sector by V2. So the interesting thing is that these anti-symmetric sectors have the same right moving R charge as the maximum Tweety sector, which will play an interesting role later. The effect of the first order supercharge is acts on states with given quantum number Hj, J tilde, is to generate states with quantum number Hj, J tilde plus half. Here, more or less focus on following the convention in Gabriel and Nart. So combining with the previous slides that was about the effect of a Q action about drawing cycles and splitting cycles, we can use a Q action to induce these following three coaching complexes. So one immediate consequence of writing down the coaching complex is that for the states that are left moving, right moving, anti-symmetric, these are all of them are automatically BPS. All of them are protected from liftings, and yeah, none of them will just get any anomalous dimensions. So here, when I write down a supervalue coaching complex, I mean that Q action acts on states in the Tweety sector can map them to the states in the maximum Tweety sector. Then you can act another Q on the Tweety sector, then you can split the cycle into the Tweety sectors. So now we have turned on the deformation. We want to understand what's the effect of the deformation. So let me present what does this deformation really do for your symmetric product orbifold. The best way to present the effect of deformation is actually by focusing on the primaries of the superconformal algebra. D1D5 system has a contracted into 4x4 superconformal algebra, and therefore it's convenient to organize all the states into primaries and the descendants. Okay. So after we restricted to the primaries, here I drew a plot of the quarter BPS primaries. So on the left side, it's the degeneracy of primaries in different sectors at the orbital point. So clearly we see that maximally Tweety sector, which is a V2, namely the Tweety sector, has much more states than the untweety sector, which is because I guess it's obvious. So after you turn on the deformation, so all the left moving, right moving symmetric states have been lifted. None of them will be BPS. And all the states in the left and right antisymmetric part will remain BPS. And some of the Tweety sector will get lifted, and majority of them actually will remain BPS.
Do you compute this right moving or this right hand figure?
Oh, so I turn on the deformation so I can compute because essentially I was computing the lifting matrix. So I can compute what states in the orbifold are lifted. So what kind of anomalous dimensions they got. And in another way, actually, because in my paper I focus on the Q-cohomology analysis. I focus on what states remain BPS. This in turn will tell me what states will be lifted. So I can do that plot.
And this was first order.
This is a second order lifting matrix, but first order supercharger cohomology analysis. Yeah. So essentially, this I guess agrees with what I said earlier that there's a folklore that after you turn on deformation, all the unnecessary states will be lifted. So here is one of the, I guess, evidence. So all the primaries in the previous slides in the left-right moving symmetric sectors are lifted. Why is this? So let's define. Let's fix left moving holomorphic weight and left moving R charge, and define two following matrices. Because I mentioned that the Q action acting on the Tweety sector can map to states in the Tweety sector. So I define this M2. And I and J denotes all the possible excitations at their particular quantum number. Similarly, I can define another matrix, which is N2, which basically explains how the Q action relating states in the Tweety sector and Q, because Q acts on this Twitty sector, we can split it, the cycle, and map it to the Twitty sector again. So from the previous pictures, that Twitty sector has much more states than a Twitty sector. Therefore, this M2 is mapping a space with with a very small size to a space with a very big size. And in general, this matrix is expected to be full rank, and therefore it's expected that all the primaries in this sector are lifted. However, if you look at N2, N2 is sort of like just the transpose of the previous plot. So N2 is mapping a very big space to a very small space. So therefore, one expects there are a lot of null states of these matrices. Therefore, this explains why there are a lot of unlifted states in the Twitty sector. Good. So let's summarize what I said about the effect of the deformation. So all the primaries in this space and in this space are lifted, and all the primaries in these two sectors are unlifted, and part of the primaries in here are lifted, and the majority of them are unlifted. Okay, so now we'll move to the discussion about the fortuity and monotonicity of these states, that are remain BPS after the deformation. If you guys have any questions, I think this is a good time to ask. But if not, then I'll go ahead.
If you fit it to E to the delta for 3/4, do you actually get the correct number of states that are being lifted if you try to fit it even from small n?
What
You compare the index E to the delta.
Oh, no, I didn't compare it with the index. Okay, so what I compare is, okay, let's do this. So there are two ways of, okay, so because we are at two different, okay, we have the knowledge about all the BPS states at the orbital point. So we can know what are states that can potentially be lifted, because the lifting requires some short multiplets combine together and get lifted. So after this deformation, second order deformation, you will find there is no further lifting that could happen, at least at N2 and N3. So yeah. So let's classify the core BPS cohomology classes into monotone cohomology classes and fortuitous cohomology classes. A cohomology class, a Q cohomology class at rank n is called monotone if for every n prime bigger than n, there exists a lift cohomology class at n prime of some representative such that psi prime is again a representative of the Q cohomology class. I will explain this sentence in the next few slides. Otherwise, the Q cohomology class is called fortuitous. So here, I guess one important thing to explain is what does this lift exactly mean. So I will provide 2 slides of vague intuition, and then provide maybe more precise slides to explain what that really is. So let's start with defining a stringent exclusion principle map, which is a map that relates states at different n. So what are the required properties for this map? So we will discuss about n prime into 3 and into 2 to illustrate the idea. Given a state in the Twitty sector at into 2, here UI denotes the excitations in the Twitty sector. We can append a trivial cycle to it. After we've done this procedure, this is no longer a valid state for any symmetric product orbital theory. However, we can sum over the S3 action, group action to make it a valid state in n prime equals 3. Therefore, it's natural to require that the stringent exclusion principle map that acting on this, this orbital states maps back to the N2 original states. This is one of the requirements for our map. Another requirement is that because now at n prime equals 3, the total cycle length is 3. So there could actually be possible excitations on this length 1 cycle. So we will impose the condition that the stringent exclusion principle map acting on states with non-trivial excitation in this length 1 cycle just be 0. Because here the total excitation length is 3. At N2, we only have length 2 to use, so we cannot We think this is a natural requirement. By the definition of monotons, for a given cohomology and class at n, if there exists a lift to any n prime bigger than n, such that it's representative of the Q cohomology class, then we can think what kind of computation we need to check. So concretely, a monoton cohomology class, one computation one needs to do is that given a particular cohomology class, then we ask if the following condition can be met. So like we start with a cohomology class at n equal 2. We append a trivial cycle to it, and we ask whether there could be other non-trivial excitations at n prime equal to 3 that's annihilated by the string inclusion principal map to mix with the original state, such that you remain BPS. Good. So let me formalize what I said. I think of previous slides is a bit vague. So the Hilbert space Hn is a quotient of Hilbert space Hn infinity by certain equivalence relations. This is what we explained in the beginning of the talk. And we also explained that each Twitty sector can be labeled by the integer partition of n, and the first cycle shape T. So In here in the D1D5 system is that the requirement that total length of the cycles with non-trivial excitations is bigger than n. So this In, when you put it here, then you can construct all the Hilbert spaces at different n. So monoton states are states that that's BPS for all n, but for twitters, there are some restrictions by this equivalence relation. One of the some components of the equivalence relation. So and it stops being BPS.
So can you explain the equivalence relation again? What is IN?
Oh, here, this one.
Yes. Is that the yes?
Oh, so I explained that I guess all the states can be labeled by a cycle shape T. But for the cycle shape T, there could be some less one component which might not have any excitations. So I denote this In as if the total length of cycles with non-trivial excitations bigger than n. So yeah, is this clear? Okay, great.
Can you define other uplifts? Like why choose this uplift?
N
equals 4, I think it's more natural to understand what the function of n is of operators. Here, is it that easy?
Can you repeat the question?
Yeah, you chose one uplift from n equals 2 to n equals 3 and
I'm not choosing one lift because I said that earlier, for example, there are a lot of operators that actually literally be killed by that map. So it's not a unique lift.
Right, well how would you choose a different one?
Oh, I could choose a different one. Okay. I'm saying that this uplift is that you will not provide you a unique sequence of operators, but it can provide you a sequence of up. Yeah. So you can have multiple sequence. So I'm not restricting to a particular sequence. I'm just asking the question if a particular cohomology at a small n can be lifted to a cohomology class at a bigger n. So, but there could be multiple lifts, certainly. Yeah. Good. Let's see what's the expectation for these N2 states and how to distinguish them into fortuitous and monotons. Okay. So we found all the BPS states at N2. Now we want to give them an interpretation. Recall we defined these two matrices which match some small space to big space or big space to small space. Similarly, we can ask the question, everything we lift to N3, are these states BPS? So the natural lift of this on Twitty sector is to lift it to a on Twitty sector to N3. And the natural lift of this Twitty sector and N2 is lift to operators with two cycles. One is length 2, one is length 1. So now let's look at the Q action plot again. So this time we find that M2, M3, and N3 is mapping a small space to a big space. So this will not, so, okay, this is not the most exciting part. I guess the interesting part is about this N2, the difference between N2 and N3. So for N2 and N2, because it split the single cycle to an Fortuity sector, so therefore it maps a big space to a small space. So there are a lot of no states. But for N3, there is a further joining to happen that maps a cycle of length 2 and length 1 to join to a cycle with length 3. So therefore, N3 is mapping a small space to a big space. This kind of intuition means that a lot of states that start as BPS at N2 will no longer be BPS at N3 because again by this picture.
None of this expectations depend on the fact that you took T4, right?
Oh, that's right. This is a vague expectation. I will justify my expectation, but normally it's hard to justify this expectation. I will use my results to justify this works. So okay, good. So what's the result? The result is that all the states in the 1,1 S1, and S2 are monotons. Like in the Fortuity sector, like left moving, right moving symmetric sectors are monotons. We check this up to H equal 4. H is the homomorphic weight. And all the monoton states in the Fortuity sector are the descendants of the half VPS primary states. And by the way, here all the monoton states are also the half VPS primaries of the descendants. The descendants of the half VPS primaries. And all the Fortuitous states in the Fortuity sector are unlifted BPS, quarter BPS primary states and their descendants. So what does this mean? I guess this has a very interesting correlation with one of the conjectures recently made by studying the BPS states in the SYK model. So Qimei Chang, Yimei Chen, and Bisong Xie and Zhengbin Yang, they studied the Fortuity in the SYK models. So what they conjecture is that fortuitous classes in a holographic theory are sharply concentrated in one space of the supercharged coaching complex. Interestingly, we find that indeed for the D1D5 system, that all the fortuitous states concentrated on a single space, like in the middle of the coaching complex. All of them has right moving R charge equal to a particular constant value. Another way to view this R charge concentration conjecture is that if we think about the bulk black hole, we find the bulk BPS black hole actually also satisfies this linear charge constraint. So I guess yeah. Okay. I also have another slide about the R charge concentration. We also studied the N-3 supercharged coaching complexes. I guess please don't read these three different coaching complex. The result is that all the fortuitous states are in the middle of the coaching complexes, and all the monotons can spread over all different spaces.
Where does this expectation come from for the lower two coaching complexes?
Oh, sorry, what do you mean?
Well, I think you computed it for the long.
Yeah, okay. Maybe I shouldn't say these tools. Yeah. Let's just focus on longest. The tools I have some vague data, but I didn't for this systematically analyze. So for N2, it's true that for all the coaching complexes, but for N3, I checked for the longest, and indeed that all the fortuitous states are in the middle, and yeah. By the way, another important thing is that note that there is another coaching complex N3 that only has a particular one component. So all the states in this sector are automatically BPS. So this is a natural generalization one can do to any large N. So you can construct any BPS states for free just by this kind of a type of argument. Good. So I'll conclude the R charge concentration, and then I'll move to discuss about the global symmetries. So
do you expect just one solution also in N equals 4 S flat?
for superamials, I think there's a debate. Yeah.
I thought the argument was general enough.
I guess the problem is I can justify my argument in using my result, but in N4 somehow it seems like there is some contradictions.
being justified using T4, like on T4.
Yeah. For example, I use my comargin analysis to justify my intuition about this big matrix and a small space. But into full supernomials, I guess I know that for example, people like James and Yang believe this R-charge concentration is true, but people like Schwartz and Minwala believe it's false. So I don't have any opinion about it.
Do you know why you believe it's wrong?
So Schwartz, they have constructed some certain type of bulk Susy solution. Yeah. So they think this kind of okay. I'll provide a simple argument about why a subset of Fortuity states concentrate at any n. So this argument will be based on global symmetry. So I found this argument in D1D5, but I don't know if I could generalize this argument to other holographic models. But let me explain how does this work in the D1D5. Besides, they preserve the super conformal algebra contracted logic into 4.4. There is another two extra global SU2s preserved by the deformation. One way to interpret them is because these BPS states we take a zero binding and zero momentum, so there is a SO4 rotating four different bosons. And these two extra covariants preserved by the deformation were constructed by well, I read these two papers, but I'm not sure if they are earlier papers. So therefore, this means orbital states can further be classified by these global symmetry representations, which actually simplify the analysis a lot. So the punchline about the conjecture is that within a given coaching complex, supercharged coaching complex, there are states transforming in the largest global symmetry representation is fortuitous. I'll explain why this works. So the intuition is okay. I draw a very bad plot, but let me explain what this means. So first of all, the supercharge itself transforms in a very small representations of that global symmetry, and the next step is to take the into two supercharged coordinate complexes, and we plot the representation size of different states, because we can group the states into different representations. So we find there are some states in this treaty sector with significantly larger representation size than the treaty sectors. And we also notice that the supercharge itself transforms in a very small representation. So this I use a red line and the yellow line to connect states that could be related by the Q action. But these states drawing a blue circle certainly couldn't be related to any other states in a 3D sector by the Q action. So these states will automatically be supercharged closed. You can argue that it's automatically Q dagger closed as well, but by the same argument. So this hopefully this justify that these states are BPS. Now let's try to argue these states are fortuitous. So let's increase and see what happens. So as we increase to n to 3, the original 3D sector is no longer the maximally 3D sector. So there will be some new maximally 3D sectors with length 3 appearing at n to 3. So if we look at the same plot again, the previous states that couldn't be related by Q to any other states now could be related by other states in the maximally 3D sector. So therefore, the representation the argument does not beat these states being Q closed anymore. So then that's I guess this is the intuition when we made that conjecture, and this is indeed true for all the examples we studied. There are a lot of fortuitous states that are transforming under the largest representation, and they are simply just this kind of type. We expect that as n increases, this type of states, at least the ratio of this type of states will decrease.
So just so I understand, this is an argument that holds for like the longest coaching complex, but for
I think that also works. But
it also works.
As long as there's a scale separation, like because in the shorter coaching complexes, there is also something like in the middle you have a lot of states, but in between you don't have enough states to hold that representation.
Right, so this is again the circle state.
Yeah. So I expect any coaching complex can use this argument to argue some automatic BPS states.
Right, and so this will this argument also tell you that the R charge will be the same also in the other coaching?
Oh, so because yes, this will essentially tells you all the largest representations are in the middle of the coaching complex. The reason is because in the middle you have the longest. Usually in the middle you have the longest cycles. So and you a largest rep actually normally comes from states that's in the maximum utility sector because this. Excitation modes also carry this global symmetry representation. So if you want to build a very big representation, it's better to act a lot of fractional modes on the
Right, but it doesn't say anything about the value of the R charge.
It tells you right moving R charge. Because in the middle it's okay. So the position of the coaching these elements are actually labeled by right moving R charge.
Right. So if I draw the same plot for like one of the other coachings.
Yeah.
Will it be centered around the same R charge?
Yeah. So all the centers have the same right R charge. Yeah. Okay, good. So I'll summarize and say some outlooks. So the finite lesson is that there is a sharp distinction between fortuitous cohomologies and the monotone cohomologies at finite because some cohomology classes can have a lift to larger n, but another don't. So fortuity cohomology classes concentrate in the middle space of the coaching supercharged coaching complex, while monotone cohomology classes don't. And also, we provide an argument that a subset of fortuitous states are states that transform under the largest rep under the global symmetry. One question that I'm intrigued is that I don't know if there is other holographic systems that can have fortuitous states that are constrained by the similar type of global symmetry argument. Good. So from the bulk perspective, okay, now I want to argue some relation between the fortuity and the black holes. From the bulk perspective, black hole macrostates obey the strong R charge concentration, while the smooth horizonless geometries don't. So it supports the proposal that fortuitous states are, can describe black hole macrostates. Let me provide another further check. Another check is that black holes, they are expected to be maximally chaotic quantum systems. One signature of the quantum chaos is the level repulsion of the energy level. However, if we want to check the level repulsion of energy level in BPS sector, it's not possible. Well, it's possible because there is no level repulsion. All the BPS sectors have the same energy and therefore do not exhibit level repulsion. There is a cute picture from the paper by Yimei Chen, Henry Lin, and Steve Shanker. They argue that since the fortuitous states have the ancestor as a non-BPS parents, so it's natural to assume that the chaos property of these fortuitous states also inherit from their parents. Therefore, it seems like because we are talking about fortuity at small n, so the natural step is to ask if their non-BPS parents display any signature of quantum chaos at finite n. So I did this computation at this lifting matrix analysis at n to 3. This plot is for the lifting matrix at h equal to 4, I think. Here I plotted I got all the anomalous dimensions and I took a look at the level space nearest neighbor level spacings, and indeed I find that there is a signature of a level repulsion here, and moreover, the distribution of the nearest neighbor level spacing is captured by the Gaussian or orthogonal ensemble. So the expectation is that somehow at finite n, these fortuitous states also could also display the chaotic behavior, but that's all the evidence I find. So hopefully I could return to this point later. Thank you. I think that's all I want to say in this talk.
ask about this last plot that you showed?
Yeah.
Is it related in any way to like this notion of LMRS replace chaos?
Oh, so their notion is a bit different. I was planning to study it.
They have the similar plots.
Right. So the point is that now I'm computing the lifting matrix eigenvalues. What they propose is that so you consider some matrices like right. So maybe you consider following matrices. So I and J, all of them are like both of them are Fortuity states. Like you fix energy and you fix R charge, so you can get the space of all of them, and you put a very simple operator in the middle, and you analyze the eigenvalues of this matrix. So I think their proposal is that if this matrix provides this picture that this have some interpretation that Fortuity states are chaotic.
Right. So there is some relation to Fortuity.
Yeah. You mean mine?
Well, both.
Oh yeah. Their proposal is to study the sandwich between Fortuity states, but I studied the non-BPS sector, like near BPS sector. I more precisely I studied the orbifold state BPS states that's being lifted, and I look at their anomalous dimensions.
Is it clear that this is not the same physics? Because what they're like.
I hope they are same physics. I don't know how to make that precise.
What you have to see, if you have random operators are not protected anymore, you can also see some.
Oh, you mean this operator?
The computation you're doing, so it's not protected anymore, and so the spectrum is something chaotic. Okay, fine.
Oh, I guess. Okay, so there are. I guess one could distinguish the states into three categories. One is states that are orbifold BPS but deformed BPS. One is orbifold BPS but deformed non-BPS, and one is orbifold non-BPS.
What does that matter? Are you doing the competition free? I don't understand. What does it matter what they are, the free form, the orbifold form?
Oh, as orbifold, they don't matter. But I'm just trying to say that this near BPS. If I denote the near BPS states as states that are orbifold BPS but lifted, I expect it's not near BPS states are the parents of these fortuitous states, because of a level repulsion. Yeah. So actually, in fact, this is true. I mean, in some sense, this is true because because we can start with this Fortuity states at, for example, at x2. We can ask what are their parents at x3, because all of them will not be BPS, and in fact, all of them are just near BPS states. So I analyze their chaos property. I hope their chaos property can invade at x2. But certainly this computation needs to be done. But I still haven't done it.
Could you remind me, the supersymmetric galaxy solution that these people construct, are they smooth horizon-based geometry, and do they exhibit R charge concentration?
I think perhaps let me not explain that here because I'm not expert about that. So, but I can say something afterwards.
I thought also there was recently some noise about hairy black holes also in history.
Oh, I can give some comments about that later. Yeah.
In 3D.
I think in 3D you will not violate our charge concentration. I can provide you my argument later.
All right, we can save that for the discussion. Let's thank Haoyu again.